Thank you very much. So what I want to discuss is some of the work we did on looking at rapid screening for toxins in seafood. And as Monica has quite rightly said, we're looking at the regulated toxins. So these are toxins such as PSP, the paralytic shellfish poison, Sakitoxin and its multiple analogues, DSP, looking at oxalic acid, dinophysis toxins and acid, and also then ASP domoic acid. And for these particular toxins, we already had in our armour highly sensitive antibodies. Again, these are antibody-based tests or immunoassays that we have used and to be highly successful in detecting these toxins, right down at picogram or nanogram per mil levels. And for these regulated marine toxins, if they basically are within the shellfish, they actually survive the whole way through from the bivalve supply chain, right through to retail to the consumers. And if you look at this supply chain, it's a rather simplified version of the chain. But there are different nodes where there can be what is described as HACCP points or hazard analysis and critical control points, where perhaps toxin in shellfish could actually be picked up before it actually gets to a retailer or a consumer. And very much the hope is that the test can be used as the primary producer to prevent these toxins entering into the supply chain at all. So for the methodologies, we started this work some time ago in developing rapid methods for toxins when the mouse bioassay was still the method of choice as a reference method. That is now being phased out with HPLC and LCMS methods. But as most of you are well aware, laboratory-based analytical methods, they might be highly sensitive, but they also require expensive equipment, they require trained experts, and they're not necessarily suitable at shellfish sites. Just as yet, we haven't managed to get an LCMS onto a boat. That may come in the future, but at the moment, just not yet. So the technology then that we looked at was a platform by Biodiagnostics. And what we call this is the second generation lateral flow device, because this allows singleplex assays to be developed. So that's individual assays for each of the toxins, but also multiplex assays, whereby a number of the different toxins can be detected simultaneously. And depending on how this particular methodology is set up, any type of biochemical immunological assay can be set up within the cartridge. And this particular cartridge fits into the reader a bit like toast in a toaster, and we can read the results relative to the toxicity as determined in the sample. And this work we had previously looked at for looking at multiplex detection and harmful algae, and it was deemed as a very sensitive method for being able to detect toxins in the water and toxins from algal cultures. So what we wanted to do was to look at this particular methodology and approach to be able to detect toxins in seafood produce. So we took the technology, and just to give you an idea of how simple it is, really we add sample to the assay buffer and we load this into the cartridge, and then 5 or 10 minutes later, it's very simplistic in terms of its use. And you can get a difference in result where when you have a zero result in terms of no toxin present, you get a nice bright signal. And whenever you have some toxin present, that signal diminishes. And it kind of works along the competitive inhibition assay for immunological methods. So what we have done in this case, we have immobilized the toxins onto the cartridge. Samples and the antibody are mixed together, added to the cartridge. We incubate a secondary antibody with a label, and we add that to the cartridge then as well. The light basically is directed to the bottom of the cartridge with the reader, and that allows excitation of the fluorophores in the labeled antibody. The sensitive detection of binding events in the cartridge is then determined and observed, and the results then are printed out onto an Excel spreadsheet. When toxin is present, as I mentioned before, there's reduced antibody binding to the surface. So when toxin is present, you get less signal. So we have antibodies available, as I mentioned. And some work we did originally was to look at Tetrodotoxin, again, because it was an emerging toxin. And with Tetrodotoxin, we looked at oysters and mussels, and we get very good correlation with some contaminated samples we had obtained from the Netherlands with LCMS-MS, and we were delighted with this type of result. In relation to, we got slightly higher values, marginally higher, but we think this might be because of some of the other Tetrodotoxin analogues that could perhaps be present. We looked at validating this method. It was very much a simple dilute and shoot method, whereby we took 1 gram of shellfish, we added 4 mils of buffer, we diluted it, and then we added it to the cartridge along with the antibody. And we were able to get good sensitivity in mussels, whereby the sensitivity we were achieving was down in around 10 nanograms per gram. And again, in oysters, similar sensitivity in around 10 nanograms per gram. So we were very much in line then with trying to meet the EFSA regulation or EFSA guideline of 44 nanograms per kilogram as deemed safe. Using the same extraction method, then we looked at the paralytic shellfish poisoning toxins, so Sakitoxin and all its family. And you can see here, we looked at Sakitoxin in relation to its toxicity equivalence factors, and whereby these particular toxins and the antibodies that we used were able to pick up Sakitoxin relative to their toxicity, as well as relative to the amount of toxin present. When we looked at matrix effects, we didn't see many matrix effects within the sample. And we also moved away from centrifugation, where we have this page bag with a filter in the middle. So we can take our sample, we can put it in the bag, and we can roller the bag with what is like a small paint roller. And that really does the homogenization step. And it also does the centrifugation filtration step. And we can add the extract then directly onto the cartridge. And again, with this particular method, we got very good correlation with the mouse bioassay and with the Lawrence HPLC method that was used. And when samples were deemed positive, they were also deemed positive by all of the methods and negative with all of the methods. So the next toxin we looked at then was azaspiracid, because to date, there's no real method out there for azaspiracid that can be used in the field. Now, for this particular toxin, it's much more lipophilic, so it doesn't necessarily like being diluted in buffer or water type systems. So we had to sort of prepare a mixture of methanol for the extraction to see how it would work. We also compared it in mussels and oysters, and we did get very good sensitivity in terms of the detection levels. We were detecting down at 4 nanograms per gram. We did some validation work with some known samples we were able to obtain. And again, when azaspiracid was present by LCMS-MS, we were able to detect it in the shellfish using the MBio platform, both in mussels and also both in oysters. In relation to this particular toxin, we still like to optimize a little bit further some of the sample preparation for better correlation. The next toxin then we looked at was domoic acid. And again, domoic acid, we were able to use the exact same sample preparation method as for Tetrodotoxin and Sakitoxin, so we can put them straight onto the chip. And again, we had very good sensitivity for domoic acid, both in shellfish and mussels and oysters. And this is kind of, the last toxin in terms of combining onto the chip. So the optical biochip then, we're working very hard towards the final array. And the final array, we will have Sakitoxin, Tetrodotoxin, ocadaic acid, domoic acid, and azaspiracid there. And the technology then is very much successfully used for the detection of regulated and emerging toxins in algal and shellfish samples. Just to summarize, for singleplex assays for each of the regulated toxins, we very much can use this particular chip that can be used out in the field because we designed the sample preparation to be simple and effective. We have a singleplex assay for the emerging toxin Tetrodotoxin, and the technology is evaluated and proven fit for purpose for shellfish samples. The technology is evaluated and proven to be fit for purpose for validation requirements is also quite important for European legislation to be using tests within the field. And we're very much working towards the final optical chip. And that's kind of where we've got to. We did prepare a flyer along with Biorex, you know, about the technology for more information. And we also have a video available as well if anyone else would like to see how we work. And thank you very much.